Welcome to ScienceCover.com. In this session we look at pressure and volume. We'll look at how the pressure and the volume will be related to each other, describe what happens to the particles when we change pressure or volume, and we'll use the equation that the pressure multiplied by the volume is equal to a constant value. First, pause the video and try the do now task. Let's check our answers. When Robert Brown studied pollen grains suspended on water, what did he notice happening? The grains jittered or moved around in random directions. Why did Einstein say this was happening? Water particles are too small to see with a microscope, but we can see the pollen grains. The water molecules are moving around and striking the pollen grains, and the random motion of the pollen is a result of these collisions. Explain how increasing the temperature will lead to a change in pressure. As the temperature is raised, the particles gain kinetic energy. This means that they move faster and strike the surface with more force and more frequently, and this results in an increase in pressure. Why do aerosol cans carry a warning saying keep out of direct sunlight? The sunlight will raise the temperature, giving the particles more kinetic energy, which will raise the pressure inside the can. Question 5. What happens to the temperature of a gas when it's compressed? If a gas is compressed, then the temperature of the gas will increase. Now let's look at how pressure and volume are related and describe what is happening in terms of the particles. This diagram shows us a gas trapped inside the syringe. We can compress the gas by lowering the top layer. This forces the particles of the gas closer together. This results in more collisions between the particles and the wall of the container each second, increasing the pressure on the gas. We can use the equipment on the screen to investigate the relationship between pressure placed on a gas and the volume of space that gas takes up. Using a foot pump, we can increase the pressure on the oil, coloured here in yellow. We can then read the value of this pressure at the pressure gauge. As the oil is a liquid, it cannot be compressed. However, the gas in the chamber can be compressed, and so we will see a decrease in its volume. We can then compare the change in the pressure with the volume taken up by the gas. The results of this experiment show that as we increase the pressure on the oil, the volume taken up by the air decreases. If we plot a graph of this data, we can see that we don't get a linear relationship, that the graph actually is a curve. Pause the video and attempt task 1. Let's check our answers. Decreasing the volume of space taken up by a gas will increase the pressure of the gas. Reducing the volume of the container of gas forces the particles closer together. This increases the number of collisions between particles on the wall of the container, increasing the pressure. The relationship between pressure and volume is not linear. So the missing words are increase, closer, pressure, and linear. Write a method to describe how we could use the apparatus to find the relationship between pressure and volume. We use a valve to set the oil pressure to room temperature. record the volume of the air in the chamber at the start of the process and the pressure gauge at the start of the process. Then use a foot pump to change the pressure on the oil, and this will change the volume of gas in the column of air. Record the volume of gas in the tube at different pressures, and then keep the temperature constant throughout the experiment. Let's look at how we can use the relationship between pressure and volume as an equation. We showed earlier in the video that increase in the pressure decreases the volume. But if we multiply the pressure by the volume, then what we see is that we end up with a constant value. This shows us that there is a relationship between pressure and volume, that if we have a gas fixed in a location at a constant temperature, and we change the volume and pressure, the values when multiplied together will always give us a constant number. This is called Boyle's law, that pressure times volume equals a constant value. We can use Boyle's law in any situation where the temperature is constant, but the pressure and volume have changed. So if we look back at the syringe from earlier on in the video, and we were to say that the pressure times the volume is constant, then in the first image, if we find what the pressure of the gas is and multiply it by the volume that the gas is taken up, it should be equal to the latter picture where the pressure is higher, but the volume taken up by the gas is going to be lower. So another way to write this is P1V1, where the ones tell us that we're looking at the first picture, and the pressure in the first picture and the volume in the first picture. And that's going to be equal to P2 times V2. So the pressure in the second picture times by the volume in the second picture. Let's look at an example. A gas is stored in a container of 1 meter cubed and has a pressure of 1 Pascal. If the volume of the container is reduced to 0.5 meters cubed, what will happen to the pressure? So we've shown here in the pictures that picture 1 has got a pressure of 1 Pascal and a volume of 1 meter cubed, and that then gets reduced in the second picture to 0.5 meters cubed. And we're trying to work out what the pressure in the second picture is. So first let's set up an equation that the pressure in picture 1 times by the volume in picture 1 is equal to the pressure in picture 2 times by the volume in picture 2. And we substitute in our values. So the pressure in picture 1 is 1, the volume in picture 1 is 1. The pressure in picture 2 is what we're trying to find, so I'm going to leave that as P2, but the volume in picture 2 is 0.5. Now 1 times 1 is obviously 1, and P2 times 0.5 gives us 0.5 P2. So to find P2, I can divide both sides by 0.5. So 1 divided by 0.5 gives me 2, so I can know that the pressure of P2 is 2 pascals. Let's look at a second example. A 0.5 Pascal gas is in a 60 centimeter cubed container. The container volume is reduced until the pressure is 0.8 pascals. What is the new volume of the container? So first we can set up our equation, P1V1 equals P2V2. And the pressure in the first picture this time is 0.5 and the volume is 60 centimeters. The pressure in the second picture is 0.8 and the volume is what I want to find. Now when it comes to units, I can use meters cubed or I can use centimeters cubed for the volume, as long as I keep the volume V1 and the volume V2 using the same units, I should be okay. So 0.5 times 60 is 30, and I've been left with 0.8 V2 on the right hand side of the equation. So now to get V2 I need to divide by 0.8. So 30 divided by 0.8 is 37.5 centimeters cubed. Now pause the video and try task 1. Let's check our answers. Complete the equation for Boyle's law. The pressure multiplied by the volume equals a constant value. Calculate the final volume. So P1 times V1 equals P2 times V2. So that's 1 times 60 equaling 1.2 times V2, which means V2 is 60 divided by 1.2, which means that it must be 50 meters cubed. Part B, calculate the final pressure. P1 V1 equals P2 V2. So we got 2 times 90 equaling P2 times 30. So that means 180 divided by 30 must be equal to V2. So V2 must be 6 pascals. Calculate the initial pressure. P1 V1 equals P2 V2. So we've got P1 times 15 being equal to 6 times 5, which means that we've got 15 P1 being equal to 30. So P1 must be equal to 30 divided by 15, which is 2 pascals. A 300 centimeter aerosol can contains a liquid at a pressure of 900,000 pascals. If the entire gas is released from the container, the pressure drops to 100,000 pascals. What volume of space would the gas take up? So again we set up our equation P1 V1 equals P2 V2. We substitute in the values, so the pressure is 900,000 and the volume is 300 centimeters before. And then after the pressures drop to 100,000, and we can leave V2 in the equation because that's what we're trying to find. So V2 must be equal to 900,000 times by 300 divided by 100,000, which equals 270 million divided by 100,000, so that's 2,700 meters cubed. The 2 meter cubes of oxygen at 100,000 pascals is forced into an oxygen tank of 0.005 meters cubed. What will be the pressure within the oxygen tank? So we can set up our equation P1 V1 equals P2 V2. P1 is 100,000 and we're multiplying it by a volume of 2 meters cubed. We want to find P2, but we've got to multiply that by 0.05. So 200,000 divided by 0.005 gives us P2, which is 40 million meters cubed. A stress ball has a volume of 200 centimeters cubed when left in a room of pressure 100,000 pascals. The ball is squeezed with a pressure of 1,200,000 pascals. What will be the new volume of the stress ball? So we set up the equation P1 V1 equals P2 V2. P1 is 100,000 and we're multiplying that by 200 centimeters cubed. P2 is 1,200,000 and we're multiplying that by V2. So 20 million divided by 1,200,000 gives us V2, which should be 16.67 centimeters cubed. Six. An empty bottle has a volume of 1,200 centimeters cubed when an atmospheric pressure of 100,000 pascals. The empty bottle is sealed and taken onto an aircraft. During the flight, the cabin pressure is 120,000 pascals. Calculate the volume taken up by the bottle. So we do P1V1 equals P2V2. P1 and V1 are the pressure and volume before we go onto the aircraft, so that's 100,000 pascals and 1,200 centimeters cubed. So that will equal 120 million. And then the other side of the equation, we've got 120,000, which is the pressure in the aircraft, times by the volume that we're trying to find. So if we divide our 120 million by our 120,000, we get V2, which is 1,000 centimeters cubed. A Mars rover fills a balloon with a sample of Martian atmosphere. The balloon has a volume of 1,000 centimeters cubed, and the atmosphere has a pressure of 655 pascals. The balloon is brought back to Earth where the atmospheric pressure is 100,000 pascals. What will be the volume of the balloon? So we do P1V1 equals P2V2, and P1 and V1 are going to be 1,655, and P2 is going to be 100,000. So that leaves us 655,000 divided by 100,000, giving us V2. So V2 is going to be 6.55 centimeters cubed.